Hello everyone, thank you for joining. Speaking today are me and Damien Haysack, who lead Microsoft Azure HPC Solutions for the Americas, and Dr. Steve Lawrence from the Cooperative Institute for Research and Environmental Sciences, a research institute jointly sponsored by NOAA and UC Boulder. Today, we will review benchmarking results of running HPC in Azure Cloud, compared in 3 different studies with either a supercomputer or with AWS, each looking at a different computational science workload. With the benchmarking results, we demonstrate that HPC workloads on Azure meet researchers' requirements as an alternative or a supplement to on-prem supercomputers. We will also demonstrate that performance and scalability on Azure meet or exceed that of supercomputers and AWS. Before reviewing the results comparing on-premises and cloud HPC, it is useful to remind ourselves of the evolution of high-performance computing. HPC has always been driven by the need for faster, more powerful computing to solve critical, often global problems. The first computer capable of HPC was the ENIAC at the University of Pennsylvania. It was developed because of World War II military needs, such as calculating artillery firing tables, and was later used for code breaking and submarine design during the Cold War. Jumping ahead to the mid-1960s, Controlled Data Corporation put out what was dubbed the first supercomputer, with 500 kiloflops up to 1 megaflops, designed by Seymour Cray and others. Cray went on to form Cray Research, and in the 70s and 80s pushed the performance to more than 100 megaflops, and then to gigaflops. In the 1990s, Sandia National Lab was an early user of the Japanese computers that dominated the market for nuclear weapons research that couldn't be conducted without HPC. The Accelerated Strategic Computing Initiative, or ASCII, was created to help the maintenance of the U.S. nuclear arsenal after the 1992 moratorium on nuclear testing. The goal was to build a teraflops machine that could do nuclear detonation simulation. ASCII Red was installed at Sandia National Lab in 1996 and remained the world's fastest computer until late 2000. Petascale computing became a reality with the 2008 launch of the Roadrunner machine at Los Alamos National Lab, the world's first HPC system to hit a petaflops, or 1,000 million, which is 10 to the 15, floating point operations per second. In only 10 years, we were above 100 petaflops, with a supercomputer built for Oak Ridge National Lab to support research ranging from COVID-19 pandemic modeling to global weather and climate simulations, which takes us to the present time, when Azure Cloud became truly competitive with the fastest, most powerful on-prem supercomputer. Last year, Azure was the first cloud HPC to make the Graph 500 list in the top 20 based on ability to run data-intensive workloads. And this year, Azure took HPC on demand in public cloud to a new level, delivering 16.9 petaflops on the HPL-Linpack benchmark, measuring calculus-intensive loads. This resulted in Azure taking 4 consecutive spots in the top 30 on the top 500 list. With Azure Cloud Computing that compares favorably with performance of the fastest, most powerful on-prem supercomputers, new horizons are open for business, academia, and government. Imagine if you had HPC on demand. One advantage of Cloud HPC is the elasticity that allows you to align HPC capacity with the often spiky demand. So let's take a look at the benchmarking studies on the next slide. We will present 3 benchmarking studies today. The workloads are NAMD to simulate virus behavior, performed jointly with UIUC through the COVID-19 HPC Consortium. Cycling data assimilation for ocean and atmosphere observations, a study performed by NOAA, and computational fluid dynamics on OpenFOAM, using the classic motorbike model of airflow around a motorbike subjected to crosswinds. Moving to the next slide. The first workload that we will examine is nanoscale molecular dynamics. NAMD is known as a computational microscope because it allows a high-performance simulation of the motion of large biomolecular systems. By simulating the interaction of millions of atoms and molecules, a view is given of the dynamic evolution of the system over time. Microsoft did this research with the University of Illinois at Urbana-Champaign, UIUC. It was a team of UIUC biophysicists and computer scientists that developed the NAMD software, also inventing a new computer language to write it, with the first release in 1995. Researchers typically run NAMD on hundreds or even thousands of compute servers in supercomputing facilities, but contention for on-prem supercomputer resources is becoming an issue globally in government, academia, and industry. So, Microsoft partnered with UIUC to understand how far NAMD can scale on Azure cloud infrastructure, to provide guidance to researchers seeking HPC resources for these simulations, including those related to COVID-19 research. The picture on the lower left shows NAMD simulation of SARS-CoV-2 spike proteins on the viral envelope. The behavior of the proteins on a virus are critical to understanding its reproduction. This simulation is running on Azure HPC. We focus the benchmarking on the Azure HBV2 VMs that offer 200 gigabits per second HDR InfiniBand networking and enable NAMD to efficiently scale across hundreds of compute nodes and many tens of thousands of parallel processes. Moving to the next slide. The figure on the left shows strong scaling results for NAMD simulation on 20 million atom and 210 million atom STMV matrix systems, a standard synthetic benchmarking model based on the satellite tobacco mosaic virus. The STMV virus is one of the smallest known viruses. In fact, its entire life form can be simulated using NAMD. The 210 million atom system scales well past 720 nodes. In doing so, the Azure and UIUC teams completed the largest scale HPC simulation ever before on the public cloud, scaling across 86,400 parallel cores, as you can see in the last line of the graph on the right. This is a magnitude higher than anything demonstrated previously. For comparison, the first NAMD research in the late 1980s was done on a biomolecular system consisting of almost 24,000 atoms. Compare that with this study's 210 million atoms. And the calculation took 20 months of non-stop runtime. Shown on this slide, we compared the scaling results with a similar study performed on the Frontera supercomputer at UT Austin. Frontera is made available by the National Science Foundation for Open Science Research. You can see the results of the benchmarking with different binaries at 512 nodes. Looking at the first bullet on the left, using AVX2 binaries, performance was 4.25 versus 2.27 nanoseconds, an 87 performance boost on Azure. We ultimately scaled to 720 clustered nodes with appreciable application performance shown on the right. The conclusions from this benchmarking are twofold. Azure HBV2 clusters met the researchers' requirements, and performance and scalability on Azure met, and in some cases beat, the Frontera supercomputer, ranked the 8th fastest supercomputer in the world and the fastest at any university. This NAMD simulation research to support accelerated drug discovery can certainly be performed on powerful supercomputers like Frontera. But when capacity isn't available, this benchmarking study has proven that researchers will have the same or better performance and scalability doing their research on Azure HPC. They can now run larger scale models on Azure as they pursue critical results for global problems, especially if they cannot get capacity on an on-premises supercomputer. Now, let's take a look at a study performed by NOAA to evaluate whether cloud computing could be used for workflows with cycling data assimilation. To frame the problem that NOAA looked to address with this project, we have Dr. Stephen Lawrence of Sirius, a NOAA affiliate.
NOAA's motivation was that it doesn't currently have sufficient on-prem HPC resources to transition all of the new research to operations without negatively impacting R&D. The issue is that in order to validate the global environmental forecast system, we need to produce 30 years of ensemble reanalyses and reforecasts. For the last version, it took 2 full years using a low-resolution uncoupled model. For the latest version, we'll be using a coupled model and a higher resolution. NOAA would also like to make R&R datasets and its software stack more widely available to the external scientific community so that they can help with post-processing and tuning efforts. The question we have, is the public cloud fast and cost-effective enough?
This is Desiree again. Steve presented the reason NOAA undertook this study. We supported NOAA in the study, and I will present the setup and results and the voice of the NOAA researchers. So when I say we, it refers to NOAA and Ceres. A couple of words about the workflow footprint. Our target footprint is on the left, a high-resolution coupled ensemble forecast, depending upon the configuration between 20 and 80. Once observations in the forecast are ready, we run a suite of data simulation solvers. When the solvers are ready, we go to the next cycle and archive the results. This workflow will now configure to between 5,000 and 30,000 CPQ cores, which is too big for prototyping. So we scale down to a low resolution of 1 degree, as shown in the prototype figure to the left. This is still a scientifically viable study for a proof of concept. Throughput is about 200 CPU cores. This is a busy slide that you can look at in more detail offline. The slide shows all of the tasks that we're running in a single cycle and the CPU, memory, and I/O of these tasks. The critical tasks on the top are very high in both CPU, memory, I/O, and internode communication, so it stresses the system. Some high-level architecture considerations. We wanted to replicate our on-prem setup as closely as possible. We staged as much blob storage as possible, S3 on AWS or Azure blob storage. Both our on-prem and cloud setups use BDP buckets for input data. We used hybrid setups. All the big apps were compiled natively, and the small single nodes post-processing tasks were containerized. We use Silk Workflow Manager to manage tasks, and we use Slurm to acquire computing resources. You have a lot of component choices to make in the cloud. Our test showed that we needed to use networking optimized instances, so EFA on AWS and InfiniBand on Azure. On AWS, we had to choose between the compute optimized nodes C5N, memory optimized R5N, or generic nodes M5N. On Azure, the choice is narrower, which isn't a bad thing, and we used HPC optimized nodes on Azure. Our stack was designed for Intel compilers and chips, so we stayed on the Intel chipset. For storage, we explored Lustre. We explored network storage of AWS, EBS, and NetApp on Azure, and one interesting choice, which proved very successful, was Azure Beyond. In Beyond, each compute node has its own local disk, and Beyond makes this collection of local disks look like a single large network-connected disk. You also need to make a choice of where you're going to store the software stack. We had different ways to access the cloud platforms. Direct access with more options to configure and more work. Also, similar to other clients, NOAA is concerned about being locked into a single cloud platform. So NOAA has contracted with ParallelWorks, which is a multi-cloud platform. The problem is that the platform is rapidly evolving, and our expectations of the platform is probably 5 years too premature. One limitation was that we could not use custom images, and we were restricted to a subset of configurations. I will not show you all 4 setups, but here's one for Azure. The ParallelWorks console gives us access to the cluster. Azure Cycle Cloud creates and manages a cluster. There is a master node, compute queue, and Lustre cluster. We did not get charged for queues unless we were submitting jobs to it. For both the AWS and Azure cloud configurations, even though the cluster allows scaling up and down your compute nodes, it's impractical for cycling workflow because it takes 10 to 30 minutes to acquire the resources. A typical task is less than 15 minutes long, sometimes only 5 minutes long, so it is impractical to scale your compute up and down for cycling workflows. We built our own software stack, and managing the software stack was one of our biggest challenges. These next 3 slides show different task performance for on-prem and cloud environments. If we look at the throughput compared to the on-prem Hera system, all cloud configurations were competitive or better than compared to on-prem. Take a look at the deviation shown by the line to the right of the bars. The biggest benefit of the cloud deployments was the performance was very reliable with almost no standard variation between different cycles, while on-prem deviated by a factor of 4. Sometimes on-prem, it could take 12 days to run a one-year experiment, and sometimes it was taking us 45 days to run the same experiment. Cost and performance comparisons. Drawing your attention to the top bar, which is on-prem Hera duration, the least duration, and the best performance is Azure Beyond, the third bar. This is one of the more interesting slides around cost comparisons. We set up different configurations, 2 Azure configurations, 1 Lustre, 1 Beyond system, and 4 AWS configurations, memory optimized R5, generic node M5, compute optimized C5, and we went from Lustre to EBS storage for one of the setups. One of the things that you see is compute dominated costs on all platforms, shown in blue. To remind you, this is a very small job, only 200 CPU threads. Lustre, which is shown in orange, was the second biggest cost when we were using it. EBS was competitive and very cheap. Azure Beyond provided extremely good performance and was free. The cost at the bottom is for a year-long run. This slide shows that cloud matches Hera for scientific accuracy, with the research results coinciding for each configuration of cloud and on-prem. For lessons learned, fast interconnect was essential for DA workflows, and surprisingly, it was the DA solvers that were the biggest MPI bottleneck, not the forecast model. Scaling compute footprint up and down was impractical in cycling workflow because you have to wait to acquire resources and get charged while you're waiting for those resources. Memory optimized nodes proved too expensive. It was cheaper to provision CPUs if you needed more memory. Storage choices were very important to cost and performance. Containers are tricky for multi-node MPI jobs. You have to manage your MPI fabric inside and outside of a container, and we haven't cracked this yet reliably. Spot availability is very spotty. We gave up on trying it on AWS. When it was available, it was faster by about a factor of 3. Cloud computing performance was very reliable with almost no deviation in performance. On-prem, we had standard deviation of up to a factor of 4, likely caused by degradation of performance due to contention of resources. Compiling natively can be time-consuming, but we successfully compiled binaries on Azure and were able to move them to run on AWS. That was a very interesting data point for us. So, conclusions from cloud testing. We were able to reproduce scientific results from on-prem. Cost was affordable. Throughput matched or beat on-prem performance. For reanalysis tasks, we can envision hybrid deployments where some of our streams will run on-prem and some will be offloaded to CSPs. Our next steps are to run extensive simulations over multiple decades, to explore using spot computing on Azure. We couldn't get it to run reliably on AWS, and to develop cloud-enabled diagnostic capabilities. Thank you.
Hi, my name is Damian Hasek, and I'm a Director of HPC and AI Solutions for Microsoft Azure. Today, we will look at optimizing OpenFOAM performance and cost considerations on Azure HPC VMs. Azure offers a complete set of HPC compute VMs to address a broad spectrum of application or business requirements. And for today's presentation, we will examine HBV2 compute SKU. The Azure HBV2 virtual machines offer the highest levels of HP performance, scalability, and cost efficiency from any public cloud provider. Featuring the AMD EPYC 7v12 processor, HBV2 VMs have leadership levels of x86 core count, memory bandwidth, and level 3 cache. In addition, the 200 gigabit HDR InfiniBand network included with every HBV2 VM enables MPI scalability to 36,000 cores per job in a virtual machine scale set, and more than 80,000 cores for our largest scale use cases. And so with this abundance of resources Customers have significant configurability at their fingertips to optimize HPC workloads and even individual models for the best levels of time to solution and total cost. To illustrate this principle in action, the Azure HPC team has run the widely used CFD application OpenFOAM on HBV2 VMs with the motorbike model at a mesh size of 28 million cells. OpenFOAM is an open source CFD solver for complex models and simulations. For the motorbike model, OpenFOAM calculates steady air flow around a motorcycle and a rider. OpenFOAM load balances calculations according to the number of processes specified by the user and then decomposes the mesh into parts for each process to solve. After the solve is complete, the mesh and solution are recomposed into a single domain. Here, we can see the benefits for memory bandwidth sensitive applications like OpenFOAM using fewer cores per VM to increase memory bandwidth per core. This approach, which improves the balance of flops to bytes of memory bandwidth, results in vastly superior performance, scaling efficiency, and cost efficiency as compared to that offered by any HPC virtual machine products available via public cloud. And please note this is a medium-sized model, which means it will only scale so far before it ceases to do so linearly. Or said another way, expect such a model to scale well up to a sweet spot for which faster time to solution is achieved, but at no additional cost, and beyond which higher cost per job is incurred to achieve faster time to solution. With that said, let's take a look at the results. Figure 1 shows the raw performance data as the model is scaled from 1 to 32 VMs. At a smaller scale of 1 to 16 VMs, during which most wall clock time is spent on computation rather than communication, using 60 cores per node, or the blue line, delivers superior performance and scaling efficiency. But as the scale grows larger, scaling efficiency becomes greater when only using 30 cores per node, which is the dark green line. At the full scale of 32 VMs, not only is scaling efficiency higher using only 30 cores per node, but absolute performance is higher as well. Now, turning our eye to business considerations in Figure 2, we see how cost per job evolves with scale. Since both approaches use the same number of VMs, differences in cost are a function to which approach is more performant at a given level of VM scale. Thus, while 60 cores per node as an approach is more cost efficient for most of the scaling exercise, at 32 VMs using 30 cores per node is more cost efficient. Now let's compare the Azure HBV2 against the C5N18XL from AWS. In Figure 3, we can see the Azure HBV2 with a performance lead between 2.16 and 2.68 times set across the full range of the scaling exercise. Note that both the 60 cores per node and 30 cores per node approach offer substantially higher levels of performance throughout this scaling exercise. And also note the substantially higher levels of scaling efficiency for HBV2, which remains near linear until the very end of the exercise thanks to the superior interconnect technology. In other words, for almost the full range of the exercise, the more VMs that the customer provisions to solve the problem, the less expensive the total bill is as compared to solving it with just one single VM. And if we overlay this performance data with pay-as-you-go or on-demand pricing for each VM from each cloud provider in similar US geographies, we arrive at Figure 4, where we can see across the full range of the scaling exercise, the total cost to solution is up to 2.5 times less expensive on Azure than it is on AWS. The largest gap occurs at roughly 16 VMs, at which the cost to solution on Azure is only 40% what it would be to take the customer to solve the same problem on AWS. Cost-effective and efficiently scalable building blocks are the hallmark of a good HPC system design, enabling scientists and engineers to arrive at insights faster with minimal expense. Conversely, HPC customers have long avoided expensive, poorly scaling HPC architectures and are wise to continue to do so in the era of public cloud. In this exercise, the Microsoft Azure HPC team has demonstrated that Azure HBV2 and OpenFOAM are an excellent pairing. Azure HPV2 virtual machines give customers the ability to optimize time to solution and cost at any scale with consistently large levels of leadership over an alternative public cloud provider. Also, a big thank you to the team of contributors who made this comparison possible. And now that we've stepped through 3 examples, we'd like to pull back for a quick overview of the Azure HPC ecosystem. You know, nobody, or it's rare that someone would jump straight into an all cloud deployment scenario. And there's really a spectrum of possibilities, and the right answer varies by customer or even by workload. So whether you're moving a single application into Azure, you're adopting a hybrid configuration, or looking to adopt a cloud native paradigm, or looking to completely decom an on-premises data center, Azure provides the range of capabilities to support the widest variety of HPC workloads. Azure HPC is a complete set of compute, networking, and storage services integrated with the workload orchestration services for HPC applications. With purpose-built HPC infrastructure, solutions, and optimized application services, Azure is a leader for price performance. Additionally, Azure includes next-generation machine learning tools to drive smarter simulations and empower intelligent decision-making. Compute offerings fall into 2 basic buckets, specialized and general purpose. The specialized compute SKUs are purpose-built for HPC, AI, and visualization workloads, such as the H series and N series, all with InfiniBand RDMA backends. And underneath the H series VMs, each have different flavors tailored to specific compute or memory bandwidth needs. Same for the N series, whether you require exceptional remote desktop visualization, deep learning, or even leveraging FPGAs. And if desired, it is possible to provision a dedicated and fully managed Cray supercomputer into Azure. The general purpose SKUs cross the spectrum for standard workloads such as the D, E for high memory requirements, and F series VMs for compute-bound workloads, as well as L and M series for extreme local I/O or high memory footprint requirements. Is the portfolio of compute options in Azure allow you to maximize the full range of CPU, GPU, FPGA, and fast interconnect capabilities to reduce job time completion from days to minutes. Finally, a quick note about the HPC storage options available in Azure. First, we have roll your own, where we have all the necessary building blocks for bespoke storage solutions or to enable third storage party providers such as Cumulo, Hammerspace, StoreOne, and DDN, just to name a few. Azure NetApp Files, or ANF, which is a hyperscale configuration of all flash NetApp filers directly connected to the Azure Fabric and fully managed as a first-party service. Single management pane built in Azure, consume on-demand, spin up, spin down storage as needed, or persistent tier to blob for cost optimization. Azure HPC Cache can enable hybrid deployments via edge caching or a mix of heterogeneous storage environments. And finally, Cray Cluster Store is your dedicated and fully managed Cray storage system in Azure, co-located with compute. What's not listed here are also Azure Files, providing a managed and scalable NFS v4 and SMB file server, and NFS on Blob for integration with Azure services, terabit per second throughput scale, and cost control. Thank you for spending time with us today, and we hope you've enjoyed learning more about the possibilities with Azure's HPC offerings. With robust reliability, data security, and global regulatory compliance, Azure is the cloud that just works for HPC.